Good afternoon, class. GT501, Lecture 8, Electric and Hybrid Electric Vehicle Components, Part 2. Last time we studied key principles and operating principles of electric machines and their simple modeling approaches. And today we're going to cover power electronics and batteries or energy storage system. Power electronics. Usually power electronics have these 4 types of converters. We need power converters for multiple reasons. Depending on the selection of the motor, a converter may be required, such as DC-DC converter or DC-AC converter, or AC to DC converter. And converter is used for matching voltages. For instance, you may have a high voltage battery or low voltage battery, and then you may have motors that need high voltage with AC signal. Then you need to convert your constant DC voltages into AC, and you also need to boost or amplify voltages. This is an example. In some HEV design, the motor provides most of the traction force. Boosting motor voltage helps to improve motor power density, packaging efficiency. So usually using higher voltage gives you better performance for motors. But usually single cell batteries can only provide 3 volt or somewhere there. So you need to stack up batteries, connect batteries in series so that amplify voltages, but you can, and it's stacking up battery cells in series with too many cells is not desirable for multiple reasons. We will talk a little bit about that in the battery section, but here, let's say we have limited voltage from the battery, and we need to amplify voltage for the motor. And plus, you may have accessories or other electronic components that uses 12 volt or 48 volt devices, and you need to be able to change voltages for those devices. And then some devices operate based on DC power source, but usually traction motors are operated by AC power source. So you need to be able to generate this AC signal from DC power source. So this summarizes why we have 4 converters. For instance, here you may have DC power source, and if you want to convert that to higher voltage, then you need to use DC-DC converter. And if you want to generate AC signal from the DC source, let's say this is high voltage, this is low voltage, then you need inverter to generate AC signal, right? And you may have, for example, if you are using motor as a generator, then you have AC signal coming in to your converter, and you will need to convert your AC signal into DC battery power source, and you would need rectifier to rectify, make AC signal flat so that the battery takes constant voltage. So you have these four converters, and we'll talk a little bit about each converters. Okay, just simple brief introduction to how each converters work. Okay. This is an example of how converters are used in electric powertrain. For instance, let's say you have a AC machine, AC electric machine, and then you have a battery. These two are the main electric powertrain component you can think of right away. But this battery provides DC signal, DC voltage and current, whereas you have AC electric machine for motoring and generation. So you need a bidirectional inverter so that you can go back and forth between DC to AC, and you also may need DC-DC converter to amplify voltage if the voltage input here is different from what you have here. Plus, usually battery voltage changes as a function of state of charge. It's not huge, but it's not small either. It's not negligible either. So for instance, your voltage, so these are nominal voltage, but when you actually change state of charge of battery, those voltages change significantly. So you need a converter to make sure you provide consistent and constant voltage at the electric machine. Or you might be able to want to control voltage at the AC machine terminal, so that you can change efficiency and torque of the electric machines. Okay. On the other hand, we also must be able to charge the battery, right? So we need to be able to connect a battery to the grid. So where grid is a three-phase AC source, or single-phase AC source, then you would need a rectifier, so that you rectify AC signal into DC signal, constant signal. And then you also have 12 volt. Usually you have 12 volt electrical systems in vehicles, a lot of lightings and your infotainment systems. Many of these electrical systems are run on 12 volt or 14 volt voltages. So, but battery provides, let's say, 200 or 300 voltage. So you need to step down those voltages. Okay, so you need DC-DC converter. So you basically need all of them. You need rectifier, you need inverter, you need converter. Okay, but we want to make these converters and inverters small, compact, cheap, and efficient. So, but the technology itself is relatively mature, but making better products. People are working on, making better product, which means cheaper and lighter and efficient. So, if you want to take a look at how power electronics actually look like physically, if you open up a converter, it looks something like this. So you have three-phase AC signal voltage terminal here, and then you have high voltage input in the case of, let's say, in the case of inverter, you have high voltage input, and you have three-phase AC outputs, and then you have cooling systems. Okay, because these components you use for converters is not 100% efficient. You lose energy during this converting process. So I mean, it's relatively high, but you still lose energy, and usually that's dissipated by heat energy. Okay, so you do need cooling system. Otherwise your component, your device will become very hot, and it will be very inefficient, or even the component can fail. Okay. So I talked about 4 types: AC to DC converter, DC to DC converter, DC to AC converter, which is called inverters, AC to AC converter. So so usually we need all these 3, but not AC converter often. But sometimes you do need it when you have to convert directly AC to AC. And usually AC to AC is combination of these components. Okay. So we will cover basic operating principles of these 3 components in this lecture. So let's talk about rectifier. Rectifier literally rectify AC signal, and how does it do it? How does a electrical circuit does it is explained here. So you have a circuit diagram. Looking at left plot, you have AC power supply, and here is the load, which is represented as a resistance. And then by arranging the circuit with 2 diodes, and then you have a transformer where you have a inductance here that creates that gets power from the AC supply, which receives this type of signal. Okay, so at this node, you're getting this AC type of signal, and if you look at the circuit, then this diode actually controls the direction of the current flow. For example, if let's say you have a positive direction voltage, then you will, so diode only allows the current flow towards this direction, right? So when you have positive direction voltage and current, then the current can only flow this direction, but it cannot flow this direction. So you get this type of current flow, but when you have negative voltage signal, then the current flows this direction. Okay. So and this works as a voltage source, and your load only receives the load from the load perspective. You only get positive direction voltage and current. So you get this kind of hilly to hill positive direction voltages and currents. But obviously, you would need to somehow make this flatter, right? And there are different techniques to do that. And you can do that by switching, okay? Which is not exactly shown here. Oh, I'm sorry. You can do that by, usually that is done by capacitance, which stores some of the extra energy when your voltage go beyond some value. So that usually when you add these capacitance, those voltages slowly drop, and you will end up with this kind of voltage signals as an output towards the load. And moving to DC-DC converter, you are trying to generate different voltage. You want to amplify or de-amplify or reduce voltages, and you can do that by using switching mechanism. So so it's called buck converter or boost converter. So buck being step down and boost being step up operation. So to explain the key idea of DC-DC converter, let's say you have a load with some resistance R, and if you have DC power source, then you can control the output voltage experienced by this load can be modified by switching the circuit. For example, if you close the circuit, then you will create voltage and current to the circuit, and if you switch off, then the voltage applied will be come back down to 0, and this will be current that the load is experiencing. But this is as you can see, this is switching back and forth between on and off. So in reality, you will need inductor to smooth out this switching behavior, so that the current experienced by the load is actually relatively flat. Okay. By the way, this is a very basic circuit just to explain the key concept of these converters and the real component or products are more sophisticated than the circuit. Okay. So for instance, here you added a diode and the inductor here. So when you switch, when you close the circuit, the voltage source will be driving the current towards the load, and the current will start to increase, due to this inductance. It will slowly increase, right? And then when the current reaches some value, or if you, for a given time period T1, you switch off the switch, and then the current will start to decrease, and you can still have the current flow because you have this diode, and your current can continue to flow with I2. Okay, so you're going to repeat this process, and you can reduce the actual applied voltage to the load experienced by the load, and you can compute the average voltage computed by this equation. What it means is it's basically average of this square block. Okay, sort of kind of like that. And then there are two types of converter operations for DC-DC converters. One is pulse width modulation, and the other one is frequency modulation. This is not just for DC-DC converter, but used in many circuits. And what this means is frequency F is kept constant, and you are only modifying T1. So meaning that you're only modifying this, and the frequency is determined by this big T. So you can adjust output voltage by adjusting this T1 and T2 ratio. Okay, and frequency modulation, what it means is you are going to either fix T1 or T2, and then you are going to modify the total T. So if you fix T1 and then if you change T2, then you're going to change T, total T, big T, and then you're changing the frequency. Okay. And that's called frequency modulation. And those two are used for many converters and motor control. Okay. And this is an example of you know, what DC-DC converter efficiency looks like and how it's used. For instance, you may have fuel cell that's providing some voltage output, and then you want to be able to control that to match with battery voltage, so that you can either you can charge the battery by matching you know, the voltage output to the battery. And this is just one example of DC-DC converter. And if you take a look at this plot, you can see the power is usually, you know, above 99% when it's operating at higher power region. So if this converter is designed for, let's say, 80 kilowatts, then operating, you know, at higher power is more efficient because it's designed for that that power, weighted power. But if you operate at lower power, then efficiency starts to drop. Okay. But still, it's not too bad. But if you add these up, you know, because you have motor, you have battery, you have converter, you have, you know, inverter, so you have many components. And, you know, if you stack up these, you know, 3%, 5% losses, and, you know, by the time you actually use the energy, you're losing significant amount of energy. Okay, so you really want to keep this high. Okay. Inverter is directly related to motor control, AC machine control, and it's absolutely necessary for AC machines. And like I explained last time, you know, unless you have DC motor where you're alternating current by using mechanical, you know, device, which is a brush, right? You actually alternate current using the contact, the change in contact from the rotating motions. But AC machines, you need to provide AC voltage and current so that it matches with the rotating motion, and you can continue to provide torque. To do that, you need inverters, you know, meaning that you have DC supply, DC power supply, and then you need to convert that into alternating current output for the motor. Okay. The way it works is something like this. Okay, so you have 4 switches, and you have 4 diodes. You can, you know, this is similar to the key operating principle is similar to rectifier, DC-DC converter. So you're basically controlling the voltage, you know, direction voltage and current flow direction from alternating current to DC current from load perspective using the circuit and the switching modules and diodes, of course. So you have these pair of switch and the diode for the load. So you need 4 sets of these. You need 2 for each side of the load, 2 for the plus and 2 for the negative, positive and the negative side. And you need that because you want to be able to control the flow, like I said. So for example, you have a DC power supply terminal here. So this is always positive, this is always negative. And what you want to do from the load perspective, you want to make sure the current always flows this direction, right? So how do we do that? So for instance, well, this is half bridge inverter, which means you have two switches. But let's take a look at this one with 4 switches, which is single phase full bridge inverter. So what happens here is that if you have this D1 D2 on, then no, let's start with this one. So let's say Q1 and Q2 is on. Okay. If you have Q1 and Q2 on, meaning that you close this switch, then what's going to happen is that you're going to have this current flow towards this direction, right? And the voltage during that time, the voltage across this point, by the way, these two are capacitance. So you need some sort of buffer and you know, let this voltage increase and decrease slowly, so that current can continue to flow even if you open the switches. Okay, open the circuit. Anyway, so if you have Q1 and Q2 closed, then you have this current flow, and then during that time, you're going to have this voltage across 2 points will start increasing, and current will flow through the load. And once it reaches some value, or you can define that by the time duration, and you're going to switch off Q1 and Q2, then what's going to happen is that you're going to have current flowing through D3 and D4. So okay, so the current was flowing this direction. So now during this, let's say this is 1, 2, 3, and 4. Okay, so for the second phase, now you have these switches open, and you have this current that was flowing is now redirected to this way. Okay. And which is driven by this capacitor. Okay. And then if you move on to phase 3, you are going to close Q3 and Q4. And what's going to happen is that now we're going to have current flowing this direction. Okay, so now you're starting to have negative voltage across the load and negative current flowing through the load. Okay, and then as a last step, if you open Q3 and Q4, then you had that sort of current inertia from inductance or whatever, and now you have this type of current flow. Okay, so which is this phase. Okay, so positive but increasing current, and then positive but decreasing current, and then decreasing current at the negative region, and then increasing with negative current. So you're basically generating this alternating current from the load perspective. Okay, the load perspective, the current is flowing this direction for this time period, and then this direction for this time period. Okay, so you're now alternating the direction of the current from the load perspective. Okay, so that is illustrated right here. So I guess this is easier to follow. Okay, so please take a look at this slide and try to understand how current is flowing. And by the way, this was single phase full bridge inverter. Okay, and this was single phase half bridge inverter. But usually for AC machines, we need three-phase inverter, three-phase AC inverters, meaning that you need 3 sets of these full bridge inverters. So you need, these 1, 2, 3 load connections for the motor, and you need 3 sets of these full bridge inverters. So you have total of 12 switches and diodes, set of 12 diode and switches. Okay, and then you can generate 3-phase AC signals for AC electric machines. So if you go back, to here, you have 3-phase AC signal coming out, and this is connected to electric machines. Okay, so usually you have these 3 outputs. Okay, and you have these IGBT modules, which is basically the switches. Okay, and then you have capacitors. Okay. And then the way, but so far we had, this was a very simplified, simple operating principle to just give you an idea of how you can create this alternating current from DC power source. But to actually experience from this is not very smooth. Ideally, in order to generate maximum torque and maximum efficiency, we want to be able to provide sinusoidal, AC signal. Okay. But to do that, you need to control the pulse width to generate a sinusoidal signal. So in reality, you need these techniques to be able to create this smooth sinusoidal three-phase AC voltage and currents. Okay. When you're looking at an example, a plot generating one phase for A, and then B, and 3. So they have 120-degree phase difference, and they are alternating with phase difference. And then you're looking at different durations, switching control and durations to generate this smooth sinusoidal signal. Okay. So that's very short summary of converters, but there's separate whole semester lecture course work on the power electronics converters, and then same for electric machines. But this lecture is to give you a quick idea of how these converter and motors operate. Okay, for those who do not have a EE background. Okay, so with that understanding, let's move on to battery. So batteries provide DC power source. Okay, and it's electrochemical device. Again, we're not going to dive into details of how battery works, or in the level of electrochemical level. Instead, we're just gonna give you a quick overview of how battery operates and the key characteristics of batteries, and how we can model it for this course. Okay. For the battery, and then for the lecture 9, we already have pre-recorded a video from last year, so we're just gonna share that recording from last year with you. So I'm going to stop here and provide you with those videos. Okay, so I hope you're following. So so I think up to lecture 6 or 7, it was it would have been more challenging for EE background students, but here it's much easier for EE background students, but for those ME students, these may not be very obvious because we're trying to summarize a lot of contents in a very short period of time. But like I said, this is just to give you an idea of how each component works. Okay. All right. Let's continue. Power electronics, right? And then we moved on to battery modeling, and we do have a bunch of slides, but what we are really interested in this course is this slide, because this slide explains the battery model we are going to use for electric vehicles. So if you take a look, it's called, there are many different types of equivalent circuit models. As you can see, it's called equivalent circuit resistive model, and there are multiple equivalent circuit models. And this one is one of the most simplest equivalent circuit model you can find. And this model consists of two parts, which is open circuit voltage, a voltage source, and then the resistance. So just two electrical components are supposed to describe the behavior of battery. But one dynamic model that's not included in this figure is the state of charge dynamics, okay, which is showing right here. So let's first start with battery power. So what's the definition of battery power here? Well, battery power is power across this two node, okay? And we have voltage across this two terminal. And then we have load, could be anything, right? We have current flow, right? And if we multiply this two, then we get power, right? But how can we compute this power? Well, to explain all the details, I will have to, spend more time and explain everything in detail and derive the equation. But in summary, we have basically, if you have taken physics 2 or just circuit theory, based on your, I don't know how much information, how much background you have with circuits, but basically what you can derive here is you have three elements. So by Korsakoff's voltage law, summation of these voltage across these three components should equal to 0, right? When this is a closed circuit, right? So if you derive the equation, then it becomes this equation. By the way, we need to multiply the voltage across each element with the current to get the power, right? But remember, current across all elements must be the same by Kirchhoff's current law, right? We only have one closed loop, one closed circuit, right? So current across all of this has to be the same, right? So if you multiply voltage across this and voltage across this and voltage across this, so this was originally here, but now moved here. So if this was here, this would have been 0, right? But anyway, oops. How do I use? Can't erase.
I think if you press the button on the pen, it turns into an eraser if you hold it.
Somehow it doesn't work. I'll have to figure it out later. But I still need eraser. Oops. Somehow eraser doesn't work. Anyway, so this is the equation we get based on Kirchhoff's voltage law. And if you multiply all the voltage terms by current, then you get power. This is battery power is basically the terminal power, which is the actual power used by the load, which could be, motor, right? And then this part is for the voltage source, okay? It's called open circuit voltage because the potential this source has is called open circuit voltage because the voltage, the potential it has when the circuit is open is the open circuit voltage, okay? And then if you multiply that by current, then it's sort of potential power you have from the source, okay? And then resistance is just losses, right? Just resistance. So if you take out the resistance power, then you get the terminal power, which is battery power, this term. So this one is resistance term, okay? And if you look, what's this? So this looks quadratic equation, right? We have quadratic term, then, so with respect to current, oh, by the way, we have everything known. So battery power is known, voltage, open circuit voltage is known, and resistance is known, but current is unknown. So we are trying to find this current X, right? So this is quadratic formula we can use, and we can compute current, right? And so now we have current. Now what? What does this mean anyways? Well, the input to the battery model is battery power. Think of it as battery power, commanded, or battery power consumed. Then what this is saying is we need to calculate current based on that value using resistance, open circuit voltage. Okay. We could also compute power, battery power, using current and resistance and voltage, but this is backwards, okay? And then once we find battery current, then now what? Well, we are interested in state of charge, right? What is the definition of state of charge? 재원 학생? 스페이스바?
배터리의 남은 잔량을 의미합니다.
네, 그걸 테크니컬하게 조금 더 정의를 해줄 수 있을까요?
처음에 노미널 캐패시티가 있다고 했을 때 사용한 전류 양만큼을 적산해서 사용한 용량을 빼면 현재 남은 배터리의 잔존 용량을 알 수 있습니다. 그걸 SOC라고 합니다.
네, 맞습니다. 근데 조금 더 그 definition 자체에 대해서 조금 살펴보면, so if we think about the definition of state of charge, literally, what's state of charge, right? Well, state is state. What is charge, right? Well, charge here is, sorry about that. How much charge we have means how much coulomb we have. 죄송한데 지금 강의 중이라서요. 네. 한 30분, 네. 네. 네, 죄송합니다. Anyway, so charge is what we are trying to count. We want to estimate state of charge, right? And charge means how many coulombs we have in the battery. What is current? Current is coulomb divided by time, right? So this is charge rate, charge per time. So if you want to count, if you want to find out how much charge you have, you need to integrate current. Then you get charge. And this is what that is. Or by that definition, state of charge, if you take derivative of state of charge, then it's current. Current divided by battery capacity, okay? And if you take integral of that, then you get this equation, okay? So that's how you compute state of charge. And sometimes this is called Coulomb counting, you know, how much Coulomb has moved through the load is you're basically counting using integrator, okay? So this will show up one more time in lecture 9. So we'll talk a little bit more about that, okay? I have few more slides, but I think this is less important for our needs, but just take a look. I will move fast here. I think we looked at this slide before. So this is how battery is used for different types of electric vehicles, hybrids, plug-in hybrids, and EV. So for EV, we use battery as main source of energy source, right? So you deplete the energy from the battery. But for hybrids, battery is used as a temporary energy buffer, right? Temporary energy storage, right? So usually your SOC swing, it's called SOC swing. So SOC changes within this band or window for hybrids. And main energy source comes from the internal combustion engine. How about plug-in hybrid? It's somewhere in between hybrid and EV, right? So for plug-in hybrid, you use battery, you deplete the battery. You use battery as a main source of power and energy. So you deplete the battery first, and then you use it as a temporary energy buffer, which is this range. So this is the hybrid mode, and this is EV mode, okay? And this one compares size of the battery for different levels of electrification, okay? This one is this figure shows rough cycle estimation of different battery technologies, okay, as a function of cycles. So and this is I'm sorry, as a function of SOC swing. So meaning that we are trying to relate cycle, which is how many cycles we can get out of a battery as a function of different SOC swings. Okay. For example, if you use your battery 70% every day, let's say you have a smartphone, right? And then every day you use your smartphone 70%. You know, by the time you go to bed, you use 70% of your battery. Then you have 70% SOC swing, right? Then you get about 4,000 cycles, okay, in theory. And then if you use 50% every day, then I'm sorry. Yeah. So if you use 50% every day, then you would use 4,000 cycles. But if you use 70%, then you will have about, I don't know, 25 or 2,000 cycles here. So this tells you if your SOC swing increases, your battery cycle life decreases, okay? So I suggest you charge your battery often, okay? If you want your battery longer and keep it healthy, okay? I tell my wife this all the time, you know, charge often, but she never listens. She uses her phone all the way down to 0, and the phone dies, and then recharge from 0 to 100%. So she has 100% SOC swing, and then she looks me like, you know, engineer, you know, such an engineer. So that's a tip about how you should use battery. This is, I'll skip this part. Okay. Okay, let's move on to lecture number 9. Okay.